Okay, now we are going to get into the core material of the course. And first, we are going to start with the non-cooperative games. In particular, we start with the strategic, or the same normal form game. And we only write what are the strategies without writing out the details of the strategies, so that we can concentrate on the basic properties of the interaction without getting into the exact order and the dependencies of the behavior of one player based on what the others have done and what that player knows and so on. So we assume, as I think throughout all the course, unless said otherwise, that the players are all rational. And moreover, the rationality is common knowledge, which means that everyone is rational, everyone knows that everyone else is rational, everyone knows that everyone knows that everyone else is rational, and so on. So rationality is the assumption which is known to everyone. It's, let's say, it's a fact which is known to everyone. And we consider, generally speaking, a strategic form game, which, as we already saw in the first lecture, on the first 4 hours, that it's a tuple. It's a tuple made of capital N, which means N, a finite number of these N players, a strategy set Si for each player, and the strategy set of all the players, or the set of all the possible strategy profiles S. It's simply a Cartesian product of the strategy set of the first player times, in the sense of the set product, the strategy set of the second player, and so on till the last player. And finally, of course, the utility functions. We assume that all this exists, so we already assume that's granted, where a utility function of agent I is a function given from the strategy set of the strategy profile, the set of strategy profile S, to the real numbers. So given what is the realized strategy profile, the utility of a player is basically a real number which tells how much agent I enjoys that profile. In particular, we are going to concentrate on so-called solution concepts. That's a very, very abstract term. And so we are going to zoom in into something concrete very quickly, but it's important to understand where we sit in the general domain. So we look at profiles, at the profiles we can expect. Often these are going to be profiles we deem stable in a certain sense. For example, Nash equilibria, which we soon define, are stable in the sense that nobody has a motivation to deviate unilaterally. So we of course have an infinite number of ways to define what we mean by stability, but there are only a few of very, very classical solution concepts which everyone knows, and also those solution concepts, such as most famous in Nash equilibria, are flawed sometimes. So they only fit certain, they require certain assumptions. There is a lot of critique over them. So that's important to know them, important to know what are the assumptions, so what are their limitations. But let's get into that. So the solutions in general, and again, we were going to quickly say this is the solution we are looking at, or these are the solutions we are looking at. But in general, the solution that's a set of these are a set of strategy profiles in S that is defined for a given game by a function, and the function is called a solution concept. So the function basically encodes what we deem by a proper outcome of the game. What do we think is going to happen there? Formally, but as I said, that's a very, very high level of abstraction, but we need to know and understand that. That's not hard. For any number of players, and for any number of strategies of player 1, k1, and so on till kn, the number of strategies of player, the solution concept, some solution concept f, is a function from all the set of games over n players, such that the first player has k1 strategies, the second player has k2 strategies, and so on till kn strategies. And given such a game, for any game with n players and k1 till kn strategies per player, f returns a subset, perhaps an empty subset, of the set of all the subsets of the possible strategy profiles. In other words, a solution concept is a function that gets a game and returns a set of all the profiles which this concept defines as reasonable, as stable. And this set can be empty, so it can be that this concept says there is no stable set for this game. This concept can be all the 2 to the power, all the sets, so that this concept says, it can be S, my apologies. So this function returns a result in 2 to the power of S. I just got confused in the notation. So see, 2 to the power of S is the set of all the sets of S. It's the same as, it's a power set of S. So the function gets an element in the subset of sets. That is, it returns a subset of S. And as I said, this can be, in general, a solution concept for a given game may return the empty subset. In other words, it may claim that for this game, according to that concept, there is no stable state. It can also return the whole S as a subset. It can claim that all the profiles are stable. And we are going to see examples, or even Nash equilibria, the most famous solution. So sometimes people say that, okay, for this game, there are no Nash equilibria, so the set of equilibria is empty. And for some game, it will say, okay, here all the profiles are Nash equilibria. Of course, these are not very interesting games, usually, so sometimes they are. Anyway, in general, solution concept for any game, it returns a set of profiles which it says are stable according to the philosophy of that concept. And of course, that's philosophical, or let's say definitely not a mathematical question, which solution concepts are reasonable. It's more related to economics, to social psychology, how people or other entities behave. But we also can define some reasonable stuff. We can sometimes guess what is reasonable. And we study what are their properties. That's the main part of mathematics. So given something, given a model which I hope fits reality, we study the properties of that model. So we are going to consider 3 solution concepts today, all very classical. One is the most classical, Nash equilibrium. And E is going to both denote Nash equilibrium and Nash equilibria in plural, the word. It also is sometimes going to denote the set in mathematical notation of all the Nash equilibria, and it will be always clear what I mean. Now we're also going to look at the dominance in the sense that something is a set of dominant strategies. Of course, it rarely exists, as we're going to see. We have not yet defined what it means, a dominant strategy, formally. But it's quite natural intuitively to say that something which dominates everyone else is rare. And another very classical thing, we're going to define being strictly dominated. So the opposite at least colloquially said, from being dominant. And one of the reasonable things is to delete everything which is strictly dominated. In the next iteration, delete everything which has become strictly dominated, and so on, till nothing is strictly dominated. And again, we're going to see this in detail. So we kind of delete everything which is not good, and whatever we are left with is this solution concept. That's also a classical thing. So we're going to look at those concepts, and we're also going to see what is the price, in a certain sense, of assuming certain solution concept. So we assume that players have to play something. It means that we limit ourselves to some strategy profiles. We say this is going to be playable, this is stable, and all the other profiles, we deem them unreasonable. Now, it means that we are not going to have them. Maybe we lose some socially useful profiles. Maybe we don't. When do we use them, lose them? When don't we? When we lose the socially best profiles, why? What exactly is the ratio between what we can get now under the kind of auspices, under the rules of this solution concept, and what we could have got in the beginning? So all those notions are related to the price of, let's say, assuming we play Nash equilibria. And the second, so that was the second. So what I started by telling that we're going to talk about non-cooperative games in the normal form. In particular about Nash equilibria, dominant strategy equilibrium, and the result of iterated elimination of strictly dominated strategies. And let us begin. But we are very organized, so we are going to first formally say what are our points, what is the plan for today. Okay, so we have done already the introduction. Then we're going to define the Nash equilibria and exemplify it, and then to define how much we lose because we constrain ourselves to Nash equilibria. What is the price of that in a certain sense? Then another solution concept. We need to define what it means to be strongly or weakly dominant for a strategy. And we are going to look at a very classical important example, which can be a topic for a course of its own, but now we are going just to look at it as one example. Second price auction, which is often looked at with valuations which are private. And the nice thing is that despite of that, we can analyze that and predict what the players are going to do, the players being the buyers, the bidders. But in this case, for didactic purposes, we're going to assume that the valuations are public, that they are common knowledge, that they are commonly known, the valuations, simply because we don't want to get out of the realm of common knowledge game. And I want to say that they are commonly known. So commonly known valuations. Good. Okay. So that was for the strongly or weakly dominant strategies. And the last solution concept for today will require us first to define the so-called mixed strategies. Now that's going to be useful and important anyway, but now we're going to work with the original strategies of the game, or in other words, the pure strategies. Unless I say it's pure, but we are going to need this definition only to define the strongly or weakly dominated. So a strategy can be strongly or weakly dominated, and that definition requires the definition of a mixed strategy. And then we are going to see this to define the solution concept I mentioned, which is the result of the elimination of dominated strategies. Okay, so basically Nash equilibria, then strong domination or weak domination, and then strong or weak being dominated. So the most famous solution concept is Nash equilibrium. So given a game, any yes. Given any game, players n, strategies s1, s2 till sn, and to the players, and the utilities 1 till n, and Nash equilibrium is the following. Profile s1 till sn is a Nash equilibrium if no player can benefit from a unilateral deviation. Formally, for any player and for any possible deviation, for any player and for any possible deviation Si prime, the utility that the player would get, given that the others keep playing what they play, S minus I remember that S minus I is the sub-profile of the strategies of the players except I. And so the utility that the player would get if she switches to Si prime will be never more than the utility it used to get before, UIS in the original program. So the deviation is not profitable for that player, given that the others play whatever they used to play. And that's something defined by John Nash. And John Nash, you may have heard about him in particular because there was a famous film where Russell Crowe played him. Now that film admittedly does not exactly follows the life events of the scientist and definitely does not give justice to the notion of Nash equilibrium. Yeah, they try to speak about that, but they definitely don't do a good job on that. They don't even budget the topic. They simply don't give any reasonable explanation about that. But it's still a nice film. Anyway, let's go to the material. So having defined what a Nash equilibrium is, let us look at the example. So it can exist, it cannot exist sometimes. So both options exist. So for example, a very simple example, this traffic coordination game. So if both players play L, so both go on the left side of the road, they're both fine, 1-1. The same if both go on the right side of the road, they don't have any preference, they just need to have the same side. But if one is right, the other one is left, or one is left, the other one is right, whatever, they have a chance to collide. Therefore, they both get -10. So they just need to coordinate. That's why it's called the coordination game. And we have a Nash equilibrium, even more than two equilibria here. So you're welcome to stop the video and think which, simply by checking all the possible profiles, whether they're equilibria or not. And of course, LLL are equilibria, because given that player L, nobody can deviate and benefit, because any deviation will not only not benefit the deviator, it will strictly decrease her utility. Anyway, LL is the equilibrium, RR is an equilibrium. Of course, RL or LR are not equilibrium, because actually in those cases, any deviation would strictly increase the utility of the deviator. Not only hers, but the important is that it will definitely strictly increase the utility of the deviator. So these and these are not equilibrium. And now let us look at a simple classical example of a game where there are no equilibria. It's called matching tennis. So you need to choose between two options, and the other person checks the same. So if you both have chosen the same option, 0-0, then player 1 gets 1, and the second player 2, or the column player gets 0. So if they both have chosen 0-0, or if they both have chosen 1-1, then the row player gets 1 and the column player gets 0. On the other hand, if they both have chosen different numbers, so if it's 1, 0 or 0, 1, then actually the situation is opposite. So player 1 gets 0 and player 2 gets 1. And here there is no Nash equilibrium. Because in any case situation, for example, in 0, 1, there is someone, actually exactly one player, who gets 0 and who can get 1 by deviating. So here the raw player gets 0, and if it changes from 0 to 1, we get 1. And the same here, or not the same, but similarly here. Player 1 gets 0, but if he plays 0, it could get 1. Here, player, or not player 1, the column player now, they could deviate and get 1. Now, the row player can deviate and get 1 instead of 0. And now the column player again can deviate and get 1. And here we already have said that the row player has a beneficial deviation. So there is no Nash equilibrium here. Now, in order to speak about what we lose in an equilibrium, what we lose because we have constrained ourselves to think that the players are going to play the Nash equilibrium, we need to define the notion of what is the social utility, not the personal, but the social utility from a given profile. So it's called social welfare, and we use a very classical notion of social welfare, so there are others as well. So given a game, players N, strategies S, and utilities UI, and a profile S1 till Sn in S, the social welfare of this profile is the sum of the utilities of the players in this profile. So we define how much the society is well off by simply summing how much every player is well off in this profile. Now, that's only one of the possible definitions. That's the so-called utilitarian definition, which we are going to mostly use, but you can also think of other definitions. There is, for example, I think it's called the active equity definition, despite that it is a kind of a bad word, but what it means is that we care about the welfare of the worst off. So we look at the minimum of the utilities. And then instead of maximizing the sum, we maximize the minimum we want utility. So we want that the worst off will be as good as possible. It's max min. Here we are going to max the sum when we maximize social value. And there are other options you can think of. Why not maximize the product of those? And then we may never have someone who is very small. Definitely someone being zero, someone having a zero utility will zero everything. So there are many ways to define that. And sure, there are many arguments for the sake of each one of them, but that's more like a philosophical or political discussion. That's not something which is exact science. So let us just say we use that and then study what are the properties. So mostly we are going to use this sum of utilities. And now we define the cost of what may I have to pay. What is the price, which I spoke about, of assuming Nash equilibrium. So what the cost we may have to pay, society pays, for the players playing what is best for everyone. That every player plays what is best for her. So every player being self-interested. And that's a classical notion which is called price of anarchy. It first was defined by Kautsopias and Papadimitriou. And that is defined as the maximum social welfare in the set S, so maximum possible social welfare in all the set of all the possible profiles, relatively to the minimum social welfare in an equilibrium. So what is the worst equilibrium which can be with respect to the social welfare notion? And how many times it's worse than the maximum social welfare in general? So what is the ratio between what we could have got and what we have actually got? And that's the price of anarchy. So we pay for the fact that they play anyhow. That's why we look at the worst Nash equilibrium anyhow, which is rational for them. By the way, it's not necessarily that Nash equilibrium is the rational thing, but that's a much deeper and that's a topic which we are not going to get into. What are the epistemological assumptions, what we assume about the knowledge of the players in order to justify Nash equilibrium? That's much, much deeper than most of the things we are going to get into. So just it's enough to say that what is the price we pay for everyone playing the Nash equilibrium? What is the worst thing which can happen relatively to the best possible social welfare? Now the other option is the price of stability, and that's in a way a complementary thing, the other extreme. So that we look at the cost we have to pay for self-interest. So maybe we play the best equilibrium, not necessarily the worst, but we absolutely have to pay that. At least the maximum thing the maximum social welfare which we can get in an equilibrium is the denominator of this fraction, maximum social welfare in an equilibrium. And we look at the ratio between the maximum social welfare in general and the maximum social welfare in a Nash equilibrium, and that is the price of stability. That's the price you absolutely have to pay for this, for being in a Nash equilibrium. So price of anarchy is, in other words, the price of anarchy is the worst possible situation. The price of stability is the best possible situation. Basically, there are two extremes. And the price of anarchy, if I've proven a lower bound, then an upper bound. So what is the worst that the maximum social welfare can be relatively to the worst social welfare in an Nash equilibrium? That gives us some safety. So that as long as we know that it's some Nash equilibrium, we can never lose more than that bound on this ratio. Now, the price of stability, on the other hand, does not give us any safety. It is not a safeguard, because even if the best Nash equilibrium has social welfare, which is, let's say, even optimum, for example, for the sake of example, let's say that it's as good as the maximum social welfare altogether. However, it can be that there are other Nash equilibria, which we actually are going to play, which are much worse. So it's not a safety net, it's not a safety notion, but rather it's a notion as to, given that we may influence the player, what is the best thing we can get? So when we can hope to influence the players, what is the best thing we can get? That's the price of stability. But they both talk about the efficiency about a given solution concept. So in those formulas, we can always look at various notions of social welfare. As I said, we are looking at the so-called utilitarian social welfare. That's not the only one. And we also can look at different notions of the solution concept. So we divide the maximum social welfare by minimum or maximum of the social welfare in a Nash equilibrium. We can look at any other set of equilibria of any other solution concept in general, and then these notions will measure what happens there. By the way, of course, this is not defined for empty equilibria, for games with empty equilibria. Okay, so let's now look at some examples about the efficiency of Nash equilibria in various games. So that's a very classical, quite a classical example from this book I use throughout most of the course. Pretty much most of the course, besides the notion of extensive games, which we are going to get at later. That is the book A Course in Game Theory by Osborne and Rubinstein. And that's the game Mozart and Mahler. So they look at a couple of friends, at a husband and wife, who go to a concert. Now they have two options: to go to Mozart's concert or to go to a Mahler's concert. And they both prefer Mozart. So if they go to, they are in a way of the same taste. So if they go to Mozart, they both derive 3, while if they go to Mahler's concert, they both derive 1, and they definitely want to be with one another. So they derive 0 if they go to separate places. Here you have two Nash equilibria, 3, 3, and 1, 1. Pay attention, please, that it's a nice example that 1, 1 is a Nash equilibrium. So 1, 1 is the set of profiles. The Nash equilibrium is Mahler, Mahler. So it's a Nash equilibrium, despite that both players would be better off if they both went to Mozart, Mozart. But since any unilateral deviation will I emphasize, will make that deviator, and the other player too, but doesn't matter, get 0, because they cannot jump to Mozart by unilateral deviation. 1, 1 is also an equilibrium. So there is no profitable unilateral deviation, I emphasize. Later we're going to talk about group deviations, and then it's not going to be a group stable equilibrium, but that's much later. Actually, we call it strong equilibrium, not group stable. So here I have two Nash equilibria, and the price of anarchy is the best social welfare, 3 plus 3, when they both go to Mozart, over the worst possible equilibrium, which is Mahler-Mahler. Pay attention, it's not the worst possible profile, which would give us 0, 0, but it's the worst possible equilibrium, which gives us 1, 1, and the ratio is 3. Now the best possible thing, the best possible ratio, the price of stability, is actually 1, because here we look at 3 plus 3, the best possible social welfare in any equilibrium, in any profile. And since that's also Nash equilibrium, Mozart, Mozart, that also goes to the denominator. So the best possible ratio is 1. So the players can be optimum, social optimum in a Nash equilibrium, but they also can be 3 times worse than Nash equilibrium. So this price of anarchy tells us that, first of all, in any Nash equilibrium, they won't be worse than 3 times from their optimum. But since they could have been optimum, and they can be also they can be also 3 times worse, it makes sense to try to coordinate. That's what we have when we see a difference between the price of anarchy and the price of stability. Because if you don't see any difference, then it means that under the assumption that the solution concept is what we assume, there is not much we can do. So we need to maybe change the rules of the game, if possible. But if we see a difference between the price of anarchy and price of stability, the practical conclusion is that we can start coordinating. Now that's something which you can speak about in a paper. That's not something we usually are going to face in our exercises, where we just look at a given game and look at, and find the price of anarchy and stability. So don't worry. The practical repercussions, the practical conclusions is just something I want you to understand. It's not something you will have to make yourself, though maybe. Now the second example is the famous prisoner's dilemma, and they have this. I remind you that they both play along. They get 3-3. If they both defect, if they don't play along, which meant basically that they witness against one another and whatever in the story of the prisoners, but it can mean many things. So if they don't play along, if they defect, or if they don't care about the climate in the explanation about grazing cows and the common good tragedy. Anyway, if they defect, they get 1-1. If they cooperate, get 3-3. But if they cooperate and one actually defected, but the other one kept cooperating, then the defector gets 5, even more, and the cooperator gets the psychopath. So it's actually a formal notion, pretty much, which is 0. And the symmetric situation arises when the column player, the row player cooperates and the column player defects. So that's the famous prisoner's dilemma. Now here, the only equilibrium is 1-1. As we saw that it's better for the player to defect regardless what the other does. In particular, when the other defects, it's the best for me to defect. So defect is the only option, and it's indeed a stable option. Now, here, there is only one Nash equilibrium, so the price of anarchy is equal to the price of stability, and that's equal to the optimum profile for the social welfare, which is cooperate, 3 plus 3, divided by the optimum or the worst. It's the same because there is only one equilibrium, which is defect, 1-1. So the ratio is 3. So any equilibrium is always suffers this ratio, is always 3 times worse than what could have been. And it can be made arbitrarily right. What I mean is that if you look at the same idea of the game, but you just, instead of 3, cooperate, and 5, you just said 30 and 50, the game would maintain the same internal logic, then the ratio would become 30. And you can get anything. You can like have 3 million here and 5 million here. So in general, we can say that prisoner's dilemma can have arbitrarily bad equilibria, which is what it's about. It's about that it can be that the only equilibrium with even a dominant strategy equilibrium, as we will see, is really bad. That's what this example is about. That it can be really bad. It does not have to be bad, it can be really bad. And then we finally go to the second notion of equilibrium, which we also have pretty much mentioned, which is called the dominating strategy or the dominating equilibrium. So, or dominant strategy profile, that's another name, but let us just define something we have mentioned briefly. Now let us formally define that. So given a game made of players and strategies S and utilities U, a strategy Si of player I is it strictly dominates strategy Si prime of that player if the utility of that player when it plays Si is strictly larger than what the player gets when it plays Si prime for any set of strategies for others. Regardless of what others do, it's better for player I to play Si than to play Si prime. It means that Si is always better, so that's what because Si strictly dominate Si prime. Simple. Strategy Si is called to weakly dominate Si prime if it's always better for player I to play Si than to play Si prime, whatever the others do. But it is weakly better. So it's at least as good for her to play Si than Si prime. And there is at least one profile of the others as prime minus I, such that if that is what the others do, then it's strictly better for player I to play Si. than Si prime. So of course, if you have something which is, if Si strictly dominates Si prime, it also weakly dominates Si prime, because it means that indeed for any strategy of the set of strategies of the others, Si is always better than Si prime for play I. But weakly dominate does not imply that it's strictly dominant. Now, then we finally define what it means to be strictly dominant. So strategy Si is strictly dominant if it strictly dominates each other strategy. And it is, as we can guess, the other option, weakly dominant if it weakly dominates each other strategy. And of course, also here, being strictly dominant implies that it's weakly dominant, but not the other way around. And then we can say that if you have a profile, a strategy profile, such that every strategy is strictly dominant, that also is what we call a strictly dominant solution. So it's a strictly dominant profile. And if every strategy is weakly dominant, we call it weakly dominant profile. That's also a solution concept, despite that it's very rare to have that one strategy is always the best possible. Excuse me, that for every player, one strategy, regardless what the others do, it's always the best. If that does happen, then definitely we can assume that it's what the players play. But again, there's more of an economical or even psychological musing about that thing rather than a mathematical claim. It's definitely not a mathematical claim. That's an economical intuition, a piece of intuition. And remember that, for example, in the prisoner's dilemma, what happened? We're going to see it soon. Let me just say that in particular, if a profile is strictly dominant, is a profile of strictly dominant strategies, and definitely, excuse me, I'm confused. If a profile is a profile of weakly dominant strategies, and in particular, if it's a profile of strictly dominant strategies, then it is a Nash equilibrium. Because if each strategy is at least as good as the others, given any set of others, of strategies of the other players, then definitely that strategy is the best given some strategy profile as required in Nash equilibrium. So that's even being in the profile of weakly dominant strategies, definitely a profile of strictly dominant strategies, is a strengthening of Nash equilibrium. Does not come from being in Nash equilibrium. It's simply that it's something which is a narrow, generally speaking, concept in Nash equilibrium, stronger concept. And an example, which is again something I've seen, that here in the prisoner's dilemma, defecting strictly dominates cooperation. So defect is defect. I wrote once defect, but the strategy defect is strictly dominant, and therefore the profile of defect is a strictly dominant profile. Okay, and now we are going to look at a very famous example of first and then the second price auction.